Chapter 5, Section 4, Exponential Functions, Differentiation and Integration. All right, now since we studied inverse functions in the last section of this chapter, we're going to talk a little bit about exponential functions, which of course are the inverse functions of the natural log functions. The natural exponential function is defined, we'll start off with a review. It's the inverse function of the natural logarithmic function, f of x equals the natural log of x, is called the natural exponential function and is denoted by f inverse of x is equal to e to the x. Now y'all remember hopefully e is the irrational number, 2.71828, etc., etc., etc. And of course if they're inverses, y equals e to the x is true if and only if x equals the natural log of y. Now we're not going to get to the calculus right away, but we're going to do a quick review of some things involving exponential functions and natural log functions, one of which would be to solve equations. When we solve exponential equations where the variable is in the exponent and the base is a constant, we'd like to try to match bases if possible, but when we can't, we use the fact that we have inverse functions and that the inverse of the natural exponential function is the natural log function. So I'm going to take the natural log of both sides. Because remember, you can only take the natural log of positive numbers, and I get the natural log of e to the 4x plus 2. That means the natural log of e to a power like this, because these are inverse functions, this is just the power, or if you prefer, I can write this as the natural log of 5 and use my property of logarithms where I can bring an exponent out in front, 4x plus 2 times the natural log of e. Now the natural log of e says, the base for the natural log is base e. It says e to what power is e? Well, that would be the first. So the natural log of e is 1. So that means I have 4x plus 2 is equal to the natural log of 5. I'll subtract 2 from both sides. I get the natural log of 5 minus 2, and then I'll divide by 4. And of course, not giving myself enough space, so right here, I'll write x equals the natural log of 5 minus 2, all divided by 4. Whatever that turns out to be, we could approximate it to however many decimal places that we wanted. Now here, I have the natural log of 3x plus 1 is equal to 7, and I want to solve this. Well, I'm going to have trouble solving it unless I can get x away from this natural log. So remember that a natural log is a base e logarithm, and I can rewrite this and put this into exponential form by bringing the base over here and taking this value, this constant here, and raising it up to that power. So I get 3x plus 1 is equal to e to the 7th. Subtract 1 from both sides, e to the 7th minus 1, and then divide by 3. And I get e to the 7th minus 1 all divided by 3, and there's my answer to that one as well. Now we did this back in Algebra 2 and definitely did this last year in pre-calculus for most of you guys. So make sure that if this looks a little new to you or a little different, you're a little rusty with it, that you give this some good practice. A couple of properties of exponentials. If a and b are any real numbers, that e to the a times e to the b is equal to e to the a plus b. Remember, when we multiply and we have the same base, we add the exponents. When we divide and they have the same base, we subtract the exponents. Some more properties here of natural exponential functions, that the domain is all real numbers. You can plug anything you want in for x, but the range is going to only be positive numbers. And that the function f of x is equal to e to the x is continuous, it's increasing, and it's one-to-one on its entire domain. The graph of f of x equals e to the x is concave upward on its entire domain. Now I'm not going to be able to do a great sketch here because I didn't give myself very much room. There's more likely a much better sketch if you were to look in the book. But essentially the graph looks something like, if we have this as 1, it looks something like this, where the x-axis is a horizontal asymptote. Your graph does not touch that, and it continues going upward. You can see it's increasing, you can see it's continuous, you can see it's concave up. All right, also that the limit as x approaches negative infinity, so if I go way out here, it's getting closer and closer to the x-axis, y equals 0, so it would equal 0, and the limit as x goes to positive infinity, as you can see it goes upward and upward and upward, would be positive infinity itself. Now, little bit about some calculus here. And as I've written something cool, and of course I don't normally write something cool unless it is cool, about the natural exponential function, is that its own derivative. Not too many functions can say that. And here's the theorem that states it. The derivative of the natural exponential function, let u be a differentiable function of x. The derivative of e to the x is e to the x. It's itself. Kind of cool. And the derivative of e to the u, chain rule, is e to the u itself times the derivative of that exponent, of that function u. Now, how do we go about to get the proof of this? Well, to get the proof of this, let's see if I remember. I wrote down proof. I should remember this. Y equals e to the x. So that means that x is equal to the natural log of y. So if I take the derivative with respect to x, I get 1 on the left side, and then I have to use implicit differentiation. I get 1 over y times dy dx. So if I multiply both sides by y, I get dy dx is equal to y. But what was y? It's e to the x. So the derivative of y with respect to x is e to the x. Kind of cool. Let's try some examples. Let's differentiate y equals e to the 5x plus 3. Well, this is an e to the u, so y prime would be e to the u times du dx. The derivative of 5x plus 3 is 5. I would probably write this as y prime equals 5e to the 5x plus 3. It looks a little bit more convenient when you write it that way. Y equals e to the 5 over x, another e to the u. So y prime would be e to the u times the derivative of 5 over x. Now remember, 5 over x is the same as 5x to the negative 1. So the derivative of 5x to the negative 1 would be negative 5x to the negative 2. So this would give me y prime is equal to, I'm going to write this as negative 5e to the 5 over x all over x squared. Don't like those negative exponents when I can avoid it. One more here. Y equals e to the square root of x. It's not that much different than, it's a power. So what I'm going to do is I'm going to take y prime, that would be e to the square root of x times the derivative of the square root of x, which would be 1/2 x to the negative 1/2. Or I could write this as e to the square root of x all over 2 square roots of x. Now, here's an example where I actually are interested in finding the relative extreme of a function that involves the natural exponential function. So I'm going to take the derivative. G prime of x is equal to, well, it looks like a product rule. First one times the derivative of the second one plus the second one times the derivative of the first one, which would be e to the x, if I factor that out, x plus 1. I set this equal to 0. Well, this can never be 0 because, as we mentioned, its range is the positive numbers, but this could equal 0 when x equals negative 1. So I only have one critical number. Let's see if I have a max or a min. So here's negative 1. I take a number from over here, let's say negative 10. Plug negative 10 in. That's positive, but that's going to be negative. So I take a number over here like 0. That's positive, and that's going to be positive, so that's positive. So it's decreasing, then it's increasing. First derivative test tells me I have a relative minimum at x equal negative 1 of, now to find what my actual minimum value is, that would be the y value. I would have to plug it in for x into my function g. So g of negative 1 would be negative 1 e to the negative 1, which would be negative 1 over e. And there's my answer here. All right, well, where there are differentiation rules, typically there are integration rules, and this section is no different. The integration rule for exponential functions, let u be a differentiable function of x. Then the integral of e to the x dx is e to the x plus a constant. That makes sense because we just said it was its own derivative, so it's its own integral plus a constant. And the integral of e to the u du is e to the u plus a constant. Now you have to be careful because whatever u is, du has to be set up, and sometimes you'll have to adjust the constant, as in this first example. I have the integral of e to the 5x plus 3 dx. My u is 5x plus 3, so my du is 5 dx. So I have to adjust my constant. I'm going to need a 5 in there and a 1/5 on the outside to keep that balanced. So this is going to be 1/5 e to the 5x plus 3 plus a constant. Not so bad. Once that du is set, you're ready to go. Over here, very similar. If u is negative 4x, then du would be negative 4 dx. I've got the dx, I just don't have the negative 4. So I'll put a factor of negative 4 in there and a factor of negative 1/4 on the outside. And I get negative 1/4 e to the negative 4x plus a constant. Don't forget your plus c on these indefinite integrals. Try a few more here. This guy here is a little trickier because it looks like maybe some kind of a rational, but here's my guy, e to the 1 over x. Now, if I let u be 1 over x, then du would be the derivative of 1 over x, which is negative 1 x to the negative 2 dx, which is 1 over x squared, negative 1 over x squared dx. Well, I kind of got him here. Do you see the x squared in the denominator? I could think of this as e to the 1 over x times 1 over x squared dx. I'm trying to make it fit the form of e to the u du. So I just need to finagle a negative 1 there. And I get the opposite of e to the 1 over x, the opposite of e to the u, plus a constant. There's my guy. This one's a little bit more straightforward. Your u is x to the third, so your du would be 3x squared dx. So now I just have to, I've got the x squared dx here. I just need the 3, and I put the 1/3 there like that. So I end up with 1/3 e to the x to the third power plus a constant. Not too bad right here. So my u in this case is the exponent for my base e, so that would be the sine of x. So du would be the cosine of x dx. It's all there. There's my du. So e to the u du is e to the u plus a constant. That was the easiest one yet. Now I have a couple that I'm finishing with that are definite integrals, because you can still use the integration rule here that you've learned. And so in this case, if I let u be the exponent, which would be negative 3x squared, then du is negative 6x dx. I'm really close. I have the x and I have the dx. I just need the negative 6. I noticed that when I've done these problems here as of late, that I've been putting it right into the original problem. Finagling the constant, as I like to call it. I think I'm going to hold off on this, and I'm going to put it in this next step. I'm going to put the negative 6 in there and the negative 1/6 on the outside. I just kind of catch myself being lazy sometimes when I do that. But it looks a little bit nicer if your work is at least shown in the second step instead of attaching it all to the original problem. So now this is going to be negative 1/6 e to the negative 3x squared, all that running from 1 to 3. So now it's just a little bit of algebra here. I plug 3 in, and I get negative 27. So I have negative 1/6 e to the negative 27 minus, then I plug 1 in, and I get negative 1/6 e to the negative 3, so that'd be plus 1/6 e to the third. Oh, what a mess this is. This is negative 1 over 6e to the 27th power plus, let's see, what did I get here? Oh, that's a negative 3. I was going to say, where happened to my negative exponent? This would be 1 over 6e to the third. I guess I could get a common denominator, which would be 6e to the 27th. I'd have to multiply numerator and denominator here by e to the 24th. If I did that, I'd get e to the 24th minus 1 all over 6e to the 27th. That's kind of messy. Might be Mr. Calculator time by about the time we get to there. All right, one more to go here. And this looks like this should be an e to the u du, because I have e to the x in both the numerator and denominator. But it's not. This is a du over u. This is going to be my u here. My u is 2 plus e to the x. Well, du then would be the derivative of 2 plus e to the x. Well, derivative of 2 is 0, so that'd be e to the x dx. And I've got it. I got it all right here. So this guy's ready to go. This is going to be the natural log. Now, normally we slap absolute value bars around this u, but in this case, 2 plus e to the x is never going to be negative, so I really don't need them. I'm going to write plus 2e to the x, excuse me, the quantity of 2 plus e to the x, and that's going to be running from 0 to 1. So if I plug 1 in, I get the natural log of 2 plus e minus, if I plug 0 in, I get the natural log of 3. Now I can rewrite this because I can use my property of logarithms. I can write this as the natural log of 2 plus e all over 3, or I can get Mr. Calculator out and approximate it. So 2 more formulas, actually 4, because of the chain rule and such, but you're going to want to put these to memory. You're getting a pretty extensive list. I think in one of the previous videos I said there would be a list of all your differentiation formulas in section 5 of this chapter, but I think it's section 8 of this chapter, so I misspoke before. But anyway, give these problems a serious look. Make sure you memorize the formulas, and as always, practice, practice, practice.